Hello dear students, I, Dr. Bindiya Sharma, welcome you all to the second video lecture on UV visible spectroscopy. In the previous lecture, we have learnt about the derivation of Beer-Lambert law. In this lecture, we'll study the introduction and theory of UV visible spectroscopy. I would suggest you that if you have not seen the lecture on Beer-Lambert law, so please first view that lecture. As we know that spectroscopy deals with the study of a spectrum which arises due to interaction of electromagnetic radiation with matter. We also know that the relationship of wavelength, frequency and energy is given by E is equal to h nu or E is equal to h c by lambda. Energy is directly proportional to frequency and frequency is inversely proportional to wavelength. To obtain the spectrum, we need a light source, a monochromator and a detector. The apparatus is called spectrometer or spectrophotometer. The spectra can be obtained either as emission spectra or as absorption spectra. The detail of this we have already covered in the previous lecture on Beer-Lambert's law. When the absorption occurs in UV visible region, then it is called UV visible spectroscopy. When a molecule absorbs UV visible light, it excites the electron from ground state or the low energy state to the excited state or to the high energy state. The energy absorbed in UV visible region, that is ultraviolet visible region, is equal to the energy difference between the two levels, that is between the higher energy state called as excited state and the ground state called as the low energy state. The UV visible spectroscopy has its important role in many fields like in analytical chemistry, in qualitative and quantitative determination of compounds. The electronic energy level are widely separated and only high energy radiation, that is the radiation with short wavelength, can excite a molecule from ground state to the excited state. Therefore, this spectroscopy is also termed as electronic spectroscopy. The absorption for UV visible shows few sharp lines. The lines occur at a wavelength where the energy of an incident photon matches with the required energy which is needed to excite a molecule from its ground state to the excited state. The electronic transitions are also associated with the vibrational and rotational transitions. And this is for this reason that the broad peaks in UV spectroscopy are obtained. Let's now first understand these various energies which are associated with the molecule, that is electronic, vibrational, rotational and translational. Internal energy of a molecule, or simply we can say the energy of a molecule, may be regarded as the sum of electronic, vibrational and rotational as well as the translational energies. For each electronic level within the molecule, the energy separation is about 100 kilocalories per mole. Therefore, it requires energetic photons near about to the wavelength of 286 nanometers, which normally falls in the UV region, as the UV region has its range from 200 to 400 nanometers. Thus, measure of the absorption in this region is called as UV spectroscopy. Now, between the two successive electronic levels, there are associated the vibrational levels. The energy separation between them being the 10th of a hundredth of electronic level. Further, each vibrational level has a set of rotational levels, or rotational states, with the energy separation of the order of hundredth of that between the vibrational levels. The vibrational transition occurs in IR or infrared region, which cause the stretching and bending of bonds. Translational energy is so small and negligible that normally we ignore it. So now the energy or internal energy of a molecule is calculated as the sum of electronic, that is electronic energy, vibrational energy, rotational energy, as well as translational energy. The translational energy being very small, we are going to ignore this. So now the total energy is given by E is equal to, that is energy of a molecule associated with a molecule is can be given by E is equal to E electronic plus vibrational plus rotational. Now let's understand this by this diagram. Here we can see that these are the two levels, that is electronic levels. This is the ground state, this is the excited state. The ground state or electronic level is given by E double dash, and the electronic level is given by E dash. Now here, this is the lower energy state, this is the higher energy electronic state. Now, or the levels. Now here within these two levels, we can see clearly that there lies many vibrational levels. These are the vibrational levels V0, V1, V2, V3. In the similar manner, for excited electronic levels also, within this lies number of vibrational levels. Now within this vibrational level, between the two vibrational level lies many rotational levels also given by this E. So here we can see that this electronic transition is occurring between the ground state to the excited state, but we are getting a broad spectrum or a broad peak because of the presence of this vibrational level as well as the rotational levels. Now, the UV region of the electromagnetic spectrum, it extends from 100 to 400 nanometer, and the visible region extends from 400 to 800 nanometer. So we can say that the entire UV visible region extends from 100 to 800 nanometer. The UV region further again is separated into two different regions. First is far ultraviolet region. Far ultraviolet region extends from 100 to 200 nanometer, whereas the second ultraviolet region is the near ultraviolet region, which extends from 200 to 400 nanometer. The ultraviolet spectroscopy follows the Beer-Lambert law, and the absorbance of sample is calculated by A is equal to epsilon into C into B, where A is the absorbance, epsilon is the molar absorptivity of the sample, C is the concentration of the sample, B is the length of the or the path length of the cuvette or the cell which is used. And when the spectrophotometer produces the absorption graph, the molar absorptivity, that is epsilon, can be easily calculated. The mathematical derivation of this law we have studied in the previous video lecture on Beer-Lambert's law. When the molecule is exposed to the radiation, it tends to absorb the radiation, and as a result of this absorption, the electron gets promoted from the lower energy level or the ground state to the higher energy level or the excited state. A detector is capable of recording the wavelength which is absorbed along with the degree of absorption at each wavelength. We are using monochromatic radiation, that is the single wavelength radiation. The spectrum is plotted as a graph between absorbance versus the wavelength. The electronic transition bring about change in the dipole moment of the molecule, and the favored transition is from HOMO to LUMO. What is HOMO? HOMO is the highest occupied molecular orbital. This is HOMO, and the electron transits from HOMO to LUMO. LUMO is the lowest unoccupied molecular orbital. Now, the principle or the theory which is involved in UV spectroscopy. There exists a very close relationship between the color of a substance and its electronic structure. Whenever UV or visible radiation passes through a solution of an organic compound, it is either absorbed or it gets transmitted according to its wavelength and the structure of the molecule. The absorption brings change in the electronic state of the molecule in the sample. That is, the electrons present will be shifted from ground state to the excited state. If the electron present in a molecule are strong enough, or we can say they are tightly bound, for example, in case of sigma bonds, then the UV radiation of high energy will be absorbed. And if the other way, that is, the bonds or present in the molecules are loosely bound or they are not very tightly attached to each other, as in the case of pi bonds or in present in the unsaturated compounds, then the absorption occurs in the visible region and the substance will appear to us as a colored substance. If E0 and E1 are the energies of the ground state and the first excited electronic state of a molecule respectively, then del E is given by, that is the difference in energy between the two states. Del E is equal to E1 minus E0 or E0, which is equal to H nu, which is equal to Hc by lambda. Del E depends on how tightly the electrons are bound, that is whether they are sigma electrons or pi electrons or non-bonding electrons, and accordingly the absorption occurs in the UV or visible range. The absorption of energy occurs due to transition between the electronic energy level present in a molecule, and therefore this UV visible spectroscopy is sometimes referred to as the electronic spectroscopy. The photochemical reactions usually are carried out in this UV visible radiation only. In UV range, the absorbed molecules produces the valence electron present in the molecule to shift to their higher energy state. Potentially, three types of ground state orbitals are involved, that is sigma electrons, pi electrons and non-bonding electrons. Let's see these three electrons in details. Sigma electrons. Saturated hydrocarbon contains sigma electrons. Such electrons require more energy to get excited than that produced by ultraviolet radiation. Hence, such type of bonds, that is the sigma bonds or the sigma electrons, are not promoted to their higher energy state by the absorption of ultraviolet radiation, because they are not capable of absorbing this radiation as they are tightly bounded. For this reason, the paraffinic compounds are usually used as a solvent because they don't absorb this ultraviolet radiation. So we can easily use them as solvent. The second type of electrons are pi electrons. They are present in the multiple bonds like double bond and triple bond. And we can see their presence in the unsaturated compound or hydrocarbons like trienes, aromatic compounds. The energy of ultraviolet radiation is sufficient enough to bring the excitation of these pi electrons. So we can see the transition of these pi electrons by the absorption of the ultraviolet radiation. The third type of electrons are non-bonding electrons, denoted by N electrons. They are not directly involved in bonding between the atoms in a molecule. For example, organic compounds which contain nitrogen, oxygen, sulfur, halogens, they have lone pair of electrons on them, and they can also be excited by the ultraviolet radiations. The same is represented here. This is the lower energy level, that is the bonding state, and this is the anti-bonding state. The absorption of radiant energy or the ultraviolet or visible radiation by the organic compound in the UV and visible region takes place because of the excitation of these electrons from bonding to the anti-bonding orbital. Bonding orbital is also called as ground state, whereas the antibonding orbital is also called as the excited state. The electronic transition that takes place in UV and visible region fall into the following 4 types. Number 1 is sigma to sigma star. Second is non-bonding to sigma star. Third is pi to pi star. And last is non-bonding to pi star. The same is represented here. This is the sigma, this is pi, this is non-bonding, this is pi star, and the last is the sigma anti-bonding. Here, this shows the increasing energy. So when we see these transitions can be observed as this. The transition, the first transition which occurs, that is sigma to sigma star. That is the sigma, the electrons present in the sigma, bonding will be transmitted or transferred to the sigma anti-bonding. That is from ground state to the higher energy state. But the transition will be from sigma to sigma star. So we can see there is a large gap. So it will require more energy. Whereas the second transition, that is non-bonding to sigma star. This is sigma star and this is non-bonding. So the electrons which are present, or the lone pair of electrons, when they will get transmitted to this sigma star or the higher energy excited state, then this N to sigma star transition will take place. This will require less energy as compared to the first, that is sigma to sigma star. This normally does not occur because it is not capable of absorbing the UV radiations. Now the third transition is pi to pi star. Pi electrons are loosely held, and when the pi electrons are transmitted to their higher energy state, that is the antibonding or the excited state, the transition is named as pi to pi star transition. And we can easily see here the energy gap is small. So when the energy gap is small, this will require less energy. So again, this our ultraviolet radiation, absorption of ultraviolet radiation can cause this transition to take place. Last is N to pi star. That is the non-bonding electron present along with the pi star, that is double bonds. So again, non-bonding are loosely held, as well as they are having very least energy gap. So again, this non-bonding to pi star transition is very easily, it can take place by the absorption of ultraviolet radiation. So if we see the energy requirement, and if we compare all the 4 transition, we can see that the highest energy requirement is for the sigma to sigma star transition, then it is for non-bonding to sigma star, then it is for pi to pi star, and the least energy requirement is for N to the pi star transition. Now, next, the same transitions are explained in detail in this slide. The first transition is sigma to sigma star, as just I have explained. For example, we can take the example of methane. Methane undergoes sigma to sigma star transition. Why methane undergoes sigma to sigma star transition? Because this is alkane, and alkanes are having only sigma electrons, or they are having only single bonds which are made of sigma electrons. So this type of transition is shown by only those compounds in which all the electrons are sigma electrons. For example, saturated hydrocarbons. They require extremely high energy, and hence the transition occurs at short wavelength, because the short wavelength have the high frequency, and high frequency means the energy of the radiation will be high. And these are found in, mostly they takes place in the vacuum region of the far ultraviolet region. Example, methane. Methane can be, the absorption of methane is indicated by lambda max value of 125 nanometer. That is, the wavelength is 125 nanometer. At this wavelength, the absorption takes place. And propane at 135 nanometer. 135 nanometer. Methane absorbs at 125, whereas propane absorbs at much higher wavelength at 135 nanometer. The second type of transition is N to sigma star transition. This is a transition in which a non-bonding electron is excited to the sigma star antibonding or the excited state or the higher energy molecular orbital. They occur in the compounds which contain an heteroatom, like oxygen, nitrogen, sulfur, halogens. For example, in the case of alcohols, ethers, alkyl halides, amines, aldehydes, and ketones. They need less energy, as just now I have explained, and hence they can occur at longer wavelength than sigma to sigma star transition. The energy requirement depends again upon the electronegativity of the heteroatom, because all the heteroatom will not be of the same electronegativity. Now, how does it depend on electronegativity? Lower the electronegativity, higher will be the wavelength. For example, methyl chloride absorbs at lambda max value of 173 nanometer, while methyl iodide have the lambda max value of 258 nanometer. Why this change is taking place? Because chlorine is more electronegative than iodine. Therefore, this methyl chloride absorption is taking place at 173, whereas methyl iodide absorption is taking place at higher wavelength of 258. Lower the electronegativity, higher is the wavelength. The same happens with the trimethylamine and CH3OH, that is methyl alcohol. Methyl alcohol CH3OH absorption takes place at 195 nanometer, whereas the trimethylamine absorption happens to be at 227 nanometer. Amines absorb at lower wavelength than alcohols. Nitrogen is less electronegative than oxygen because of this reason. Now, the next transition occurs at pi to pi star transition. That is the transition in which pi electrons are involved and they get excited to their higher energy or antibonding pi star molecular orbital. Such transition is termed as pi to pi star transition. The excitation of pi electrons requires smaller energy, hence the transition occurs at longer wavelength. This kind of transition occurs in unsaturated compounds which contain double and triple bonds. And also it happens in aromatic compounds. Alkenes, alkynes, carbonyl compounds, cyanide, azo compounds, etc. show this type of transition. The unconjugated or the isolated alkenes show the absorption below 200 nanometer, and the conjugated compounds show the absorption above 200 nanometer. For example, ethylene, CH2 double bond CH2, it has its lambda max value or absorption is shown at 174 nanometer, whereas when conjugation takes place, then the compound becomes CH2 double bond CH, CH double bond CH2. Then the absorption happens at 213 nanometer. The presence of alkyl group on the double bond brings about the bathochromic shift at 5 nanometer. The shift is also known as red shift, and the shift is inclined towards the low frequency or towards the longer wavelength. The last transition is non-bonding to pi star. N to pi star transition is the transition in which the electron is excited from a non-bonding atomic orbital to the pi antibonding molecular orbital, and the transition is indicated by N to pi star transition. This transition requires least energy, hence it occurs at a much longer wavelength. All the organic compounds which contain double bond between carbon and some heteroatoms like oxygen, sulfur, nitrogen, oxygen, and any else like halogens, they can exhibit this type of transitions. For example, C double bond O, C double bond S, N double bond O, etc. So now after studying all the four transition in detail, it is very clear that the energy requirement is much higher for sigma to sigma star, and it is least for non-bonding to pi star. Now let us see some terminologies which are mostly commonly used in ultraviolet visible spectroscopy. So the characteristic energy of a transition is the property of the group or the group of atoms rather than the electrons. So when an absorption occurs, the two types of groups are there which can influence the and resulting absorption spectrum of a molecule. They can change or they can influence the absorption spectrum. And the groups are termed as chromophores and auxochromes. Chromophore, let us see one by one. First is chromophore. Chromophore is defined as any functional group that absorbs electromagnetic radiations irrespective of the fact whether it will give color to the compound or it won't give color. That is, whether it gives color to the compound or not, but this is any kind of functional group that will tend to absorb electromagnetic radiation. And there are two types of chromophores. Chromophore containing pi electrons, they undergo pi to pi star transition. For example, ethylene, C double bond C, acetylene, C triple bond C, etc. Second type is chromophores which contain both pi and n electrons, and they undergo two types of transitions, pi to pi star and n to pi star. For example, carbonyl C double bond O, nitrile C double bond N, azo, nitro, etc. Then the next is type is auxochromes. Auxochrome are termed as the groups which do not show any characteristic absorption above 200 nanometer, but when they are attached to a chromophore, they cause a shift of absorption band to a higher wavelength or to a longer wavelength. So an auxochrome is the group which when it gets attached to the chromophore, it is responsible to cause the shift or it can shift the absorption band towards the longer wavelength. Few examples of auxochromes are hydroxyl, OH group, NH2, amino, sulfhydryl or SH groups. Few of their derivatives or also act as auxochrome, that is OR or NHR, NR2 and few halogens also. For example, benzene. Benzene shows an absorption at the lambda max value of 254 nanometer, but aniline show the lambda max value at 218 nanometer. Here, the NH2 groups which is attached to aniline, because the formula of aniline is C6H5NH2. So the NH2 group which is attached to aniline acts as an auxochrome. And when this aniline is observed that lambda max value is increased from benzene is at 254 nanometer, but aniline shows the lambda max value at 280 nanometer because of the presence of auxochrome group, that is NH2 group. This is the role of the group. The group, whenever it get attached to a chromophore, like benzene is a chromophore. So whenever it get attached to a chromophore, it causes a shift of absorption towards the longer wavelength. Now let us see the four different types of shifts named as bathochromic shift, hypsochromic shift, hyperchromic shift and hypochromic shift. These terms are little bit confusing, but fine, after explanation they'll be very much clear. Let's start with the bathochromic shift, or it is also known as the red shift. The shift of absorption maximum to the longer wavelength brought by either the substitution onto the chromophore or by an auxochrome or by the change in the solvent. Again, I would repeat, bathochromic shift is nothing but the shift of absorption maximum to the longer wavelength. Whenever the wavelength gets shifted towards the longer wavelength or towards red color, that is known as red shift. So why this is happening? This can happen because of some kind of substitution which takes place at chromophore, let us say by some kind of auxochrome group or by the change in the solvent, because solvent also plays an important role in this UV spectra. Let us try to understand by taking the example of benzene. Benzene lambda max value is 256 nanometer, whereas aniline lambda max value is 280 nanometer. So because of the presence of this auxochrome, that is the group NH2 group, we can see the shift of 24 nanometers when we see the lambda max value of benzene and that of aniline. So this is known as bathochromic shift or the red shift. Now the next shift is termed as hypsochromic shift. This shift the absorption or the lambda max value to a shorter wavelength, just reverse of bathochromic shift. Why this is happening? This results because of the removal of conjugation or change in the solvent polarity. Again, solvent role is here also. For example, aniline show lambda max at 280 nanometer, whereas the anilinium ion, that is in acidic solution of aniline, we get anilinium ion. It shows lambda max value of 254 nanometer. So aniline shows lambda max at a longer wavelength at 280 nanometer, whereas the anilinium here lambda max value is getting reduced. Why? The aniline has a lone pair of electrons over nitrogen atoms, but the protonated aniline, which is termed as anilinium ion, has no such lone pair of electrons for conjugation. So here the removal of conjugation is the factor which is responsible for this hypsochromic shift. Next is hyperchromic shift or hyperchromic effect. It is an effect which results in an increase in absorption intensity. This is the auxochrome, that is the effect of auxochrome is the result when the absorption intensity tends to increase. So the introduction of an auxochrome usually brings the hyperchromic effect. Whenever an auxochrome is introduced, again let us see the example of benzene and aniline. Benzene B band is at 256 nanometer, whereas aniline shows the B band at 280 nanometer because of the hyperchromic effect of the auxochrome which is present in aniline, that is the group NH2. Last shift is hypochromic shift. This effect, because of this hypochromic shift or hypochromic effect, it results the decrease in the absorption intensity. It is just the reverse of hyperchromic shift. And this is brought by the reduction in conjugation. For example, aniline. Aniline has lambda max value of 280 nanometer, whereas we have seen that anilinium lambda max value is at 254 nanometer. We have seen the same example in hypsochromic shift. So why this is happening? Why the aniline is having the lambda max value larger as compared to anilinium ion? Because of the reduction in conjugation. So these are the 4 different type of shifts which can be seen in UV visible, or this terminology is commonly used in UV visible spectroscopy. So this is again represented by this graph, or this is E epsilon, value of epsilon, and this is the wavelength in nanometer. We can see here the curve, and when the wavelength tends to increase, this is termed as bathochromic shift or the red shift. When the wavelength tends to decrease towards the blue, it is termed as hypsochromic shift. And when the intensity or increase in absorption, or the increase in absorption intensity occurs, it is termed as hyperchromic shift. And when the decrease in the intensity is seen, it is termed as the hypochromic shift. So these were all the terminologies which are used commonly in the UV spectroscopy. Now there are some factors which affect UV absorption, and the most important factor is the effect of solvent. The solvents used in any spectroscopic method should be mostly transparent. That is, they should be non-absorbing. For example, if we are using any solvent in UV visible absorption, so it should not tend to absorb the same radiation. Otherwise, we won't get the proper results or the proper graph or the spectrum. So solvent play an important role on the absorption of the spectra of molecule. The spectrum can vary in intensity, wavelength when the different solvents are used. The polarity of solvents brings shift in the absorption spectra. The electronic transition from pi to pi star and n to pi star respond differently to the polarity of the solvents. The polar solvents, polar solvents, tend to stabilize the molecular orbital, and molecular orbital like non-bonding molecular orbital, pi molecular orbital, and pi antibonding molecular orbital to different extents. Here, the N or the non-bonding is stabilized most, and the next comes the pi star or the pi antibonding. This results in the bathochromic shift in the pi to pi star transition whenever it will take place, and to a hypsochromic shift in the non-bonding to pi star absorption band. And the same is indicated here. This is pi electron, this is non-bonding, this is pi star, this is increasing energy is indicated here. This transition happens when the solvent is non-polar. As soon as we change the solvent to the polar solvent, the transition is something different because of the change in the solvent. So the table shows the wavelength cutoffs, that is the lowest working wavelength of some solvents which is used in UV visible spectroscopy. So we can see here few examples, that is water UV cutoff in nanometer is 190, for hexane it is 200, methanol it is 210, ethanol also it is 210. And again, it goes on different. It is different for different type of solvents. So dear students, with this, we come to an end of this lecture on UV visible spectroscopy. In the coming lecture, we'll see the instrumentation and application of UV visible spectroscopy. Thank you and happy learning.